Okay, let's start today's panel session. And I'm Yoshihiro from Nagoya Institute of Technology. And today, the Professor Wada and I will moderate this panel session. And here is Wada Sensei. Please.
Hello, everybody. I'm Osami Wada from Kyoto University. And Professor Ito will lead this panel session. And my field is from the hardware. I'm in charge of the EMC evaluation of the Ethernet, so I will be a kind of supporter of this panel session. Thank you very much. And Professor Ito will introduce panelists one by one.
Okay. Thank you, Ada Sensei. So, fortunately, we have 6 panelists for this sessions. And the first panelist is Mr. Christoph. Please introduce yourself.
Hello, my name is Christoph Gollob. I'm working for BMW Group, studying automotive engineering in Austria and being 10 years now at BMW. The last 2 years in the vehicle network departments. And I will try to bring you the view of the OEM.
Okay, thank you very much. So the second panelist is Mr. Illia. Okay.
Hello, everyone. My name is Illia Safiulin. I'm representing Elektrobit. I'm working as a product manager there, dealing mainly with the product related to the effective and efficient in-vehicle communication.
Okay, thank you. So the third panelist is Mr. Christopher.
Hello, everyone. My name's Christopher Mash. I work for Ethernovia, and I lead our customer engagements and business development there. I've spent the last 15 years working with automotive Ethernet, pretty much from the very beginning. I've been very active. I've started a few of the call for interests in the PHI group, and worked pretty much through that time with all the OEMs and tier ones globally on how Ethernet changes the network, brings new features and services, and again, we'll talk about that in more detail today.
Okay, the fourth panelist is Mr. Amir.
Hello, everyone. My name is Amir Bar-Niv, and I'm working in Marvell, running the marketing of the automotive BU. Before that, I worked in Aquantia. I got into Marvell through the acquisition of Aquantia, where we designed multi-gig PHYs. So I'm working in the automotive segment for a semiconductor for the last 8 years.
Okay, thank you. The fifth panelist is Mr. Naoshi Serizawa.
Hello, everybody. I'm Naoshi Serizawa, working in the YAZAKI Corporation. And actually, I've been working for the physical layer development more than 20 years. Thank you very much.
Thank you.
Hello, this is Marty Gubow with Keysight Technologies. I've been in the test and measurement area for 25 years. Started with HP, that became Agilent, and now Keysight. Prior to that, I worked for an automotive manufacturer for about 10 years.
Thank you very much. And we have 6 great panelists today. And this is today's time schedule. And at first, I will introduce this session, and then all panelists will introduce themselves and give us their presentation. And then panelists and moderators will discuss about the theme of this panel session. And then finally, we will answer questions from audience. Finally, Wada Sensei and I will conclude this presentation. This panel session. Okay. So please sit down. So please remain here. Okay. And the theme of this panel session is Ethernet as the enabler for software-defined vehicles. And the objective and motivation of this panel session is to think about in-vehicle Ethernet as enabler for SDN. And then let us discuss about SDV or in-vehicle, so next generation in-vehicle and so on. And before this panel session, we sent many questions to all panelists. And these are the questions. So the first, why is there a need to this discussion on SDVs now? And the second, what is the state of the art of SDV articles in the automotive industry? The third, what makes a software-defined vehicle? What new functionalities are enabled with the software-defined vehicle? Fourth, which features of Ethernet-based communication are required to enable the SDVs? Five, is the different in-vehicle network architecture required to support SDVs? Six, how data rate is important for communications of SDV? And then what role do optical communication technologies play? Is the automotive optical ecosystem all set for next generation in-vehicle Ethernet connectivity? Finally, what still needs to be done to ensure a time rollout of SDV in the industry? And I expect all panelists will answer these questions based on their expertise. So we have very limited time for this session. So please, I want to start the introduction and presentation by all panelists. Please start, Christoph. Mr. Christoph, okay. Thank you. Thank you.
Slide 2. Okay. Just go to the second, or the third one. Next page. Oh, yeah. So after introducing myself, and you've seen my picture again, what you could have read on the first slide, it's also in the program. I have the honor to at least state what we are understanding on a software-defined vehicle. A software-defined vehicle is mainly software-defined in its character. So by changing the software or the software behavior, you get a different emotional experience. One easy example would be switching to sport mode. The chassis control changes, the way the vehicle drive changes, the display changes, the powertrain behavior changes. You can even go up to it changes how it smells electronically. Still, a vehicle is not a software product. A vehicle is an electromechanical product, so it's the mechanic part working together with the software. Both are important. The functionalities in a software-defined vehicle are shifting to using all available data everywhere. So the interaction is getting more and more nonlinear and complex. And here a standardized toolset, like for example Ethernet, is providing a good base to cope with this. If you're going mix and match with all different technologies, it probably will just not work. Example for the benefits of Ethernet, and this idea would be scalability, going from 10 Mbit to multi-gigabit, which you can both see on the exhibitions. Layer separation, which gives you a lot of freedom how you handle the data. You're not depending on the physical layer by defining your data model. Security starting at layer 2. You also heard a speech about this. Time awareness, which we also heard. And most important of all, I don't know if it was up to date, a seamless connection to the backend. So Ethernet is the same as internet works. So you can connect with your backend, compute in your backend. An easy example would be voice recognition in your, for example, BMW. If you tell him something and it has internet connection, it's working really, really good. This defined interfaces and the direct connection to the outside world allow to separate update cycles from the hardware. So you not have to change hardware. You can just do an over-the-air update. Next big thing on there. And the other important thing is by having standardized interfaces, you can develop your different functionalities in different speeds. At BMW, we're just setting up a program developing this for us on big scale, which is mainly driven by my boss's boss. So the idea here is chassis is more or less settled. There are not that big jumps. Infotainment, on the other hand, there are big jumps. ADAS is somewhere in the middle. I think an easy picture to understand is nothing is looking older than an old infotainment display. It's really just making the car age. And if by updating it, you can try to keep it fresh as long as possible, and you don't have to synchronize all your development cycles, but you need a stable interface. Yeah, on the other hand, you need the hardware, providing you enough headroom and for future growth, and providing you the basics, like, for example, MACsec as a layer 2 security, or the capability of timestamping, yeah, switching, everything. So where we are going, a lot of the necessary work on Ethernet has already started. Standardization of, for example, switch configuration is starting at the moment, and makes configuring switches and using them far faster in the development cycle. The specification of the MACsec profile and the integration of it on all speeds is also having one thing scaling through the whole network. Next is providing headroom. You shall not use your link to its fullest, then you don't have headroom for future growth. And what is probably becoming more and more important is also energy consumption. The usage of energy on all this computational and I would call it 12-volt system, not powertrain, is growing and growing with every generation. And therefore, it's more or less defining the range you can drive with your car and the rating you get. So, I hope this gives you a short overview on where to head and where to dive into, and what are the needs we have. So it's really a tool set which is developing. Software-defined vehicles we already have, but the software integration and the part of importance of software is growing and growing. So, thank you.
Okay, so now it's my turn. What do we see from the basic software side? So actually I will skip a couple of slides and we'll start right here. So importance of the preparation. There is a saying from Benjamin Franklin, by failing to prepare, you're preparing to fail, which means that we need to start early. We really need to start early. So the thing is that the technology and the set of feature, it's growing, and it's growing faster from year to year. For example, on the right side, you can see that we have a basis technology in the beginning, but then it grows up into multiple directions in terms of complexity, in terms of set of interfaces, and so on and so forth. And at the moment, actually, we are at the stage where both software and hardware, we're hitting the ceiling. Because with the classic, let's say with the standard approaches, we cannot cope with the demand on functionality. That is why it's exactly the time right now to introduce new technology in hardware, special hardware acceleration, and also to introduce new software which knows how the hardware is ticking, how the hardware is working, in order to provide, let's say, a very stable and very highly performant symbiosis of software and hardware. And yeah, it's exactly the time right now. So what is the state of the art of the software-defined vehicles? On the right side of this slide, you can see maybe the quite simplified view of the different parts where the software was used, and you see that it's growing, and so on and so forth. And it will be growing. Is it good or bad? I assume it is good. Otherwise, well, why do we do it? And So the most wanted features from the consumer side is, of course, the ADAS, but also there is, and the future steps, the autonomous driving. Of course, the infotainment innovation with increased amount of data to be processed, to be connected, and so on and so forth. It's also very appealing. And finally, the ability to update the functionality, ability to include new features, new, many other sites over the year, or to update not only the, let's say, the features, but also the firmware, for example, of your network and so on and so forth. It's also very nice and very important right now. And what makes the software defined? We've heard today an example of the smartphone. And I like the example, for example, personally, of the dashboard. On the left side, before we had a hardware dashboard which was quite optimized for specific hardware function, for specific functionality, where there was some special domains for, I don't know, for the speedometer, for the tacho, and so on and so forth. And in order to introduce new functionality, we had to change the hardware. We had to exchange the whole setup and so on and so forth, which was pretty challenging. Right now, by adding a software functionality on top, we can end up with a software-based dashboard where we can show whatever we want, from the speed up to, I don't know, some movies or even playing computer games on your main screen, which is quite crazy, but it's possible. And all of that is done by updating the software, which is a very good example of the software-defined vehicle. And finally, from the automotive E2E architectures, what is needed from the software-defined networking? I would say that it's a pretty tricky question, because from one side, the E2E architecture does not limit that much the usage of the software-defined vehicle. But in some cases, with some architectures, it will be easier to implement. It will be definitely easier and more efficient to implement. Because, for example, if we use a zonal architecture, where it gives us additional flexibility in comparison to the centralized architecture, because then if we need to change only a certain part of the network, we can do it locally without changing the whole parameters or without changing the huge configuration of the inside of the, let's say, main HPC in the centralized architecture. This is the main topics to be covered, at least from my perspective, from software point of view. The rest, I'm pretty sure, will be covered by my colleagues. Thank you.
Okay, so when we talk about software-defined vehicles, there's already a large number of vehicles out there that have a lot of features. And I think we're in an interesting time in the automotive industry where a lot of big changes are happening at the same time in terms of the powertrain, but also now the range of connectivity we have in the vehicle, and then the features and additions and applications we want to bring to the car. So we hear about this statement quite a lot. So in the past, cars used to drive. But now, as a passenger or an operator of a car, we want to be able to change configurations, add new services, add new features. And here's some of the changes that we see coming. So in an architecture, say, in the previous generation, each of the CPUs inside those computers had just enough headroom to run those applications. As we go forward in time, because we're now adding additional services to the car, we need a lot more compute power when we sell that vehicle so we can add additional features and services as we go forward. Associated with that, then the bandwidth that we see inside the car is also increasing. You know, we have a large number of additional sensors coming in, additional use cases, additional data types we want to move around the vehicle. A great thing about Ethernet and why we're all here is Ethernet has a very flexible speed when we're driving that into the cable, but then the software and the software stack and the higher layers is very unified, allows us to move software services and features around the car independent of speed. One of the driving factors for this bandwidth is also then the autonomous and ADAS features. And again, different OEMs are on different paths here in terms of the how we move the data into the network for processing. But as we've seen through other industries, eventually we see Ethernet pretty much everywhere in the vehicle, all the way from the core, all the way up to the edge, and everything that's interconnected. Moving forward in time as well, we have cars with huge number of ECUs today. So one of the trends we also see is consolidation of ECUs. So that brings more compute power into an ECU, and those ECUs now consuming data from multiple traditional domains. And I've got a picture that explains that in a bit more detail. And the reason we're all here, software-defined services. What does that mean? What does that enable? What does that then provide for us going forward? And ultimately, in order to provide some of these services, we need a connection to the cloud to be able to download additional software as we go forward in time. So if we take a look at an architecture today, and this is an architecture for a vehicle which is driving around on the roads at the moment. And we can see this is a traditional domain-based architecture. We have the domain controllers at the top of this network, and then they're branching out into different either data generators or data consumers at the edge. And this is showing actually all the different technologies which are in a car today, all the different traditional buses. So we have CAN, LIN, FlexRay, MOST, Ethernet, LVDS, everything that's in the vehicle. And as we know, it's very complex. It leads to a lot of ECUs in the car, big wiring harnesses as well, complex network. But now if we think about all of these ECUs and all the different software services and vendors associated with that, it's very, very complex. Having said all that, though, this is already supporting a software-defined vehicle. So that network we're just showing you has all these features here. And then the question is, what is a software-defined vehicle? So top left here, I think, is something we all associate with this. So the ability for additional software updates to be downloaded in the field to provide additional features and services, and another way for the OEMs to monetize that vehicle after it's left the showroom. The bottom left picture here shows really the whole connected car ecosystem. So as well as data inside the car, we have now connection to the cloud to provide data services for the OEMs, running diagnostics, ability to dynamically update the configuration of the car while that's in operation. Bottom right, from a consumer perspective, is the ability to download new features into that car and select them as we're driving around. And then the top right, we have the connectivity from the vehicle through the cloud to my service provider and then down to my phone to then run applications and services that control the vehicle and other kind of concepts as well. But I think what we see going forward is the level of software and services we want to provide is going to increase. So in order to do that, moving to an ability to have a more unified software that's sitting on top of an Ethernet-based network that allows us to support a network which is based on Ethernet, and this is just one example of a network. So we know that every OEM is on a different path that we've seen today in terms of where we're moving forward. But what we do see is this concept of a central compute or multiple high-performance compute ECUs in the car, which, because they are now connected into the network, are able to see data from any of the different traditional domains in the vehicle. So this allows us to have applications and services that look at data from, say, the infotainment domain, the body, chassis domain, sensors, and be able to provide new features based on that data. Zonal aggregators, again, we've heard about this today. So instead of a single ECU at the edge running data from a single domain, we now have aggregation units that take data from all the potentially different traditional domains and aggregate them into a single box. And now we have an Ethernet-based network. We can transfer all of that data very efficiently through the network, through to the compute elements. And we see all this based on Ethernet. So we've seen demos here with multiple speed grades. We now have Ethernet solutions from 10 meg all the way up to 10 gig. And in the future, we'll be talking about 25 gig based solutions as well. So having the ability to move the data around, provide a scalable network, and then the software services on top of that is one of the key reasons, beliefs that we see for software-defined vehicles. And now what gets really interesting is if we have all this data coming into our compute nodes, how do we move that efficiently from the wire through the network switching into the CPU, into virtual machines, and into host memories? And that's something that we see is going to be an interesting area for development as we move forward in time. Thank you.
Okay, so no doubt that the automotive industry is going through a major transition with regard to electronic in the car. Okay, so it started until I would say 2015 with what we call device-centric, where we added more and more electronic, like radio, with some capabilities, CD, GPS, but each system was, stand by itself, with its own controls. There was very little exchange of information between the different systems. Moving forward, I guess from 2015 and still going through this transition, we are now in what's called the application-centric, okay, where we have the different domains, okay, like ADAS, gateway, infotainment. Each one of them still has its own controller, but they are sharing information between them. But moving forward, what we see, and again, if I try to put a year, probably starting from 2025, is what we call the data and software-centric car, okay? The car that has the capability to upgrade the features, to add more application into the car, and this is what software-defined vehicle is all about. And by the way, interesting enough, if you look on data center today, you see the same transition, okay, from application-centric to, again, data and software-centric. And this is one of the reasons, that people are calling the next generation of cars data centers on wheel. Okay, so it's not only a buzzword, there is a real intention here behind this. Now, Ethernet is really providing the basic features that are needed in order to enable this transition to software-defined vehicle related to flexibility, the speed, the security, and the safety that is required in those cars. So let's talk a little bit on some of the details. So at the high level, what software-defined vehicle means is, unlike the car of yesterday, where you buy the car and then you have all the features already installed, the capability to upgrade and download new application from the cloud in order to add more capabilities to the vehicle. Okay, and first of all, it's a new business model, but this is going to be also a very successful one, mainly because of all the stakeholders that are involved in this transition are benefit from this. Okay, so starting with the OEM, which means a new stream of revenue that they can get for a car that they already sold to the final user, and over time they can generate more application that can be either developed by the OEM or by third-party companies that are going to develop it for the OEM and eventually be used in the car, and that can be related to a new application related to smart city, to of course autonomous cars. So there is a lot of application that will be developed over time that can be downloaded into the car. And then it's the car owner, okay? The car owner really enjoyed the capability to upgrade the car over time and add more features, okay? Meaning that the car value is no longer decline. And eventually it's also the service provider that enjoyed the high bandwidth that we'll need in order to support all these new applications. So this is going to be a successful business model, again, because everyone enjoyed it, and it's involved over-the-air upgrades and a new feature. So let's think for a second what it means for the car itself. So software-defined vehicle, as I said, is the capability to download a new software to the car. either enhancement for the existing features or new applications. What is needed in order to do it is a network that will be able to adapt itself to these new applications, okay, reshape the data traffic inside the network in order to serve better the new application that were downloaded into the central processors. And Ethernet is the way to do it because Ethernet is already have the capability to reconfigure and reshape the traffic inside the car, mainly by programming the switches and the bridges that exist or will be exist in the car. But in order to really benefit, okay, or really get the full benefit of software-defined vehicle, you would like to make sure that most of the components in the car are what we call talking Ethernet, okay, connected to the Ethernet network. This will really give us the full capability of software-defined vehicle. So showing an example, okay, of a car, and of course different car will look totally different, but we're showing here a zonal architecture where everything is connected to the Ethernet, starting from the central processors, through the different ECUs, the cameras and the display all connected to Ethernet, okay, to the Ethernet backbone. And then you can run all the utilities and all the capabilities that I was talking about, like reshaping the traffic inside the network from each of these devices. What that gives us, it's standard-based, okay, to start with. It's Ethernet. It has the leverage of the software. So when you move from one model to the next model, you don't need to rewrite the software, again, because everything is running over Ethernet, and Ethernet is taking care of the traffic handling between all the different devices. You have the flexibility and the scalability, so you can easily add more monitors, more ECUs, more cameras, when again, everything is Ethernet-based. And of course, you have the redundancy and safety that is part of the Ethernet network. At the high level, the features that we would like to see to realize the promise of the software-defined vehicle is the capability to do over-the-air software updates, meaning a storage in the car that will be able we can able to download all the software and firmware into this storage and be able to upgrade all the components, when the car, for example, is parking. The high-speed network of the backbone, okay, that will be able to handle all the different traffic of the different ECUs. Of course, Ethernet end-to-end, as I said, to be access to each of those devices inside the car, and eventually the requirement for security that are going to be even more and more important when we have the software-defined vehicle. So, and we'll talk more about this in the panel. Thank you.
Okay, it's my turn. I'm now Serizawa, the representative, maybe Jasper. So, so I'm typical Japanese, so that I like to answer the question from the administrator. So the one is, what is the state of the SDV activity in the automotive industry? So my idea is a cloud linkage and OTA update and contribution to sustainable society, and maybe the entire different industry. Like currently, the automotive industry is very close, but maybe the consumer electronics market or communication market supplier will be in the automotive application market. Looks like. So I'm also put some Japanese subtitles. Maybe it's easy for Japanese people to understand what I'm saying. So the next question. I must apologize. One is why is needed the discussion in SDV now? So I have no idea what is SDV, but these 4 items I'm thinking about: the changing the value of the user vehicle, and from the private ownership to sharing the vehicle. And also, the cars cannot keep up with the evolution and changes in the cell phones and maybe the people want to customize the car to my style. So this one's key. And also the number 3 question, what makes a software-defined vehicle? What now functionalities are enabled with the software-defined vehicle? So the left side, the features, and the right side, the new functionality. So the feature is the scalable software is most variable for the function, the SDB, and also maybe the improving cyber security, and also the customize. And in the new functionality means autonomous driving is mandatory maybe, and sometimes we need to access to the metaverse or virtual realities, and also the big data analysis is the new functionality will be needed. So, which feature of the Ethernet-based communication are required to enable the SDBs? So the communication is maybe the wireless Ethernet, the mandatory, and of course the wired Ethernet is necessary. But more than 10 years ago, this is a Tokyo Motor Show slide, and Toyota displayed this kind of vehicle. I'm not sure how many people remember it, but this is the concept of the SDB looks like. Okay, so and number 5 is a different in vehicle network architecture required to support SDBs. So my idea is the OTA is mandatory, but the architecture independent. So that even though the zonal architecture or domain-free architecture, but the SDB is can be possible. And number 6, how data rate is important for communication of the SDB. So my idea is that the software or data updating, maybe 100 megabit per second communication channel is good enough. But the multimedia or streaming data, maybe up to 10 gigabit second of communication will be needed. But connect between the virtual reality and the physical reality, like maybe in that case, we need the more than 10 gigabit per second communication channel is needed. So the number 7, what role do optical communication technology play is automotive optical ecosystem, all set for next generation in-vehicle Ethernet connectivity. So the feature of the optical component, fiber optic technology, is the weight saving and the power consumption saving, and noise resistance is very high compared to the electrical channel. And also, the all set for optical network, like here. So one is a standardization. The standard is available for the maybe the multi-optical communication system, and also components available. But I'm not sure the current latest situation for the microprocessor. So even though the channel is available for more than 10 gigabit per second communication, but the microprocessor is hardly to support it. It's impossible to install the vehicle. Then most important is the semiconductor or microprocessor development. And last one is what still needs to be done to ensure a timely roll out of the SDB in the industry. So one is a leadership, strong leadership by OEM maybe, and also standardization and legal regulation has to be needed so that this kind of the structure is mandatory for SDB into the market. So thank you very much.
Hello, everyone. This is Marty Gubow with Keysight Technologies. So first, I want to thank that the panel selection that they included test and measurement and instrumentation. Of course, I am last because that's usually that last thing that people think about when they're designing their vehicle is how are we going to test things. But it is great that at least we are thinking about how we're going to test things. So looking at some of the questions. So why is there a need for software-defined vehicles now? But of course, everybody wants new features. Everybody wants to generate more revenue. The whole subscription model that everybody is moving towards, that's really driving the need for these dynamic and changing vehicles. But from an engineering point of view, we used to always say, oh, the car's an engineered system. If it works when it rolls off the assembly line, we don't really have to worry about it because we're not going to be changing a whole lot. But that world is now changed. So now there's a big what if, what could possibly change? And when we look at networks in particular, a lot of times we didn't worry about the network. Best case was good enough because we over-engineered it and we knew there was enough bandwidth for all of our applications and it wasn't going to change. But now the world is changing and we have to think into the future and think what's going to be happening. So then we look at what is the state of the art of today's software-defined vehicles in the automobile industry. Well, of course, software-defined vehicles are in production today. In fact, the next question I'm going to ask, when was the first software-defined vehicle? When does it really start? But we all want to deploy new features, and we really have to start thinking of our network architectures as a design solution from the beginning. A lot of people, just assume that things are going to stay the same, but we have to use technologies such as TSN and architect the networks and kind of future-proof those networks. So as the loads change and as there's a lot more traffic, we're still going to be able to function properly. So this is a question I have for everybody. So 30 years ago, you see I have some gray hair, and I was writing software for cars. We had calibrations and bits, and we had software-defined features, and I could set one calibration value or a bit in assembler back then, and I had to change that in an EEPROM because this was before Flash. But yet, did I have a software-defined vehicle when I changed a calibration value and that changed from one trim level to another trim level? So to me, software-defined vehicles have been around since the beginning of software in vehicles. And as we had different calibration values, so this is not a new concept. When did all of a sudden we start calling this a software-defined vehicle? Okay, so we went from having to actually burn EEPROMs. That's a long time ago. Flash memory was new. That really changed the world because I could, update my ECUs. But we wanted more features, and we wanted a mobile platform that can expand, and we wanted to add ADAS features and infotainment features and self-driving. So I look at a software-defined vehicle today as a platform that really has to have 4 different items. So this is where I say the transition from maybe a software adaptable vehicle to a software-defined vehicle. Maybe this is where we can start calling it an SDV. For one, we need flexible hardware platforms. In the past, we would design the hardware specifically to the needs that were necessary today. The I/O would be exactly what was required, and there really wasn't any headroom to change that. So in today's architecture, we put in processors that have multiple cores, more headroom. We can dynamically change features. So I say we have to start at the hardware, and the hardware has to support multiple cores and expandability. The next thing we have to do is we have to look at the software architecture. We need to be able to isolate programs that are running in these very complex computers. We have to use containers and virtual machines. Because when we had very simple processors that only had one task, from a security and a reliability standpoint, we have to be able to isolate these software features. So I have to say SDVs have to have this more complex software environment that provides that isolation. And then we have to look at the network. We have to think of designing the network for the future. We have to, if we need time-critical data, we have to use TSN and other techniques to ensure that even with increased loads or different network architectures, we're still going to be able to get the reliability. So we have to really think in future-proof our network designs. And then finally, we have to provide an easier way to do updates, over-the-air updates, patch management, cybersecurity. We have to have mechanisms to make minor changes and not just reflash the whole ECU. So there's a lot of dynamics. So these 4 elements to me are required for us to call it a modern day software-defined vehicle. But I would have to say that I think the cars 30 years ago were also software-defined, but maybe in a different era and different complexities. All right, thank you.
Okay, thank you for all panelists. So please bring your chair and come up to this stage. So I'm sorry. Okay. So now we got 6 very great presentations, and in my opinion, so the name of the software-defined vehicle has the word software-defined, but in order to realize SDV, we must consider hardware update and software update. So I think, and the SDV is not for future technologies. So SDV will come us soon. But the panelist has many questions on each other. So now let us start the question and answers.
Okay, let me start the discussion first. Thank you very much for a really nice presentation. So I think everybody understand what is the software-defined vehicle and the kind of image, but and also I get some point that we should discuss to realize the software-defined vehicle. One thing is there's somebody mentioned that, of course, the software-defined vehicle is very, very good. That is very promising because we can update the software to change the functionality. So that's very nice, but also it's very dependent on hardware. And also the main part is what kind of structure we can apply the software-defined vehicle. And as somebody, Illia or somebody mentioned that we can apply the software-defined vehicle to the traditional type of domain type network and also the zonal network. But these are really different. So whether we can apply the software-defined vehicle for both of the traditional type of domain type network, or we should concentrate on the kind of zonal type. That is one point. And another thing is somebody mentioned that if we use all the Ethernet type network, that's going to be rather easy to prepare the software-defined vehicle, but whether we can include the traditional communication type like can and to use together in a simple single software-defined vehicle or not. That is probably the second point. So whether we have to move to the kind of concentrated Ethernet network, or we can continuously use the traditional type communication. And the third point is security. Probably in the present type of domain network, each domain requires each security or each response or that kind. But if we try to reconfigure the network, then what kind of network we have to prepare? That is probably the third one. So from we can start from any place. So I'd like to start from the network type, domain type, or zonal type. Somebody have some comment on that? Okay. Switch on, please.
That way. Okay. It's not just pressing. So the network is defined by its needs. That's the first thing. You're not doing an architecture because it's looking nice. There's always different aspects driving the architecture. It's needs like safety, needs like security, needs like communication channels, space, so real physical space to put the cable into. And I don't think we are doing zonal because it's looking nice. We are doing zonal because our wiring harnesses are getting too complex, and that's why we are driving into zonal. We are not doing zonal because of architecture. And the same is for legacy networks. We are using legacy networks where they are good enough and have, for example, a cost benefit, and they are not harming us. And we have to find ways to communicate with legacy networks through an Ethernet main network, I would call it. So the question is, software-defined vehicle is probably not changing the architecture. It's the demand changing the architecture, and the demand changes. Handling with legacy networks is they will not disappear all of a sudden. So we have to find a way to communicate with them through an Ethernet network. And the last thing is security. And as I already stated in my beginning, if we are going to link-based security, we have a lot of the basic security stuff already done. We have probably to separate more easy to harm networks from the main car. That's domain thinking. But probably if you can't crash a car on the over internet, it's not looking good in press. So here you have to add additional layers, but in the end you have to have, independent on how you design your architecture, you have to have a security base layer.
Thank you. So the network can be independent on that? I think it's a bit question. Okay, go ahead.
I also have a couple of comments with regards to these questions. So I fully agree that basically I fully agree that demand defines. In some cases, it's not that easier to provide the update to the whole functionality. In some architectures, it's a bit easier. Then, for example, if we consider the domain architecture, there is still communication between different domains. And let's say this software-defined vehicles can be also implemented there, but it might to put an additional gateway functionality or additional network requirements onto this inter-domain communication. With regards to the legacy networks, fully agree. We will still use the legacy networks because it is there, it's working, and it's quite often very cheap. But what can be changed in terms of the software-defined vehicles is this, let's say, gateway functionality. Gateway functionality, I mean, from the legacy network to the Ethernet. Because maybe in some cases we had one configuration that certain CAN signals had to be packed and transported to one place, and then if the configuration has to be changed, the gateway, the configuration of the gateway microcontroller or zonal ECU whatsoever can be changed. And then the same messages will be transported to another endpoint.
So you mean that we're going to use the conventional network and also the new type of software-defined vehicle, defined network at the same time, and they connecting with the switch? That is the thing you mentioned? No?
Yeah, the switches will be very important, and the software on the switches will be also very important. It is already.
So probably to change the legacy network to apply the software-defined network will be we have some problem, but the okay. So sorry, I'm a bit confused. So that's not so easy to apply all the conventional network to software-defined network. Don't you think so? You can. Sorry.
So I think we all see, certainly in the next few generations, there will be a mix of Ethernet-based networks and also legacy networks as well. And what we see really happening with the software-defined vehicle is the CAN networks will be static, they can't change. But what we then see is those CAN messages now being transported across the Ethernet network. And now, instead of those CAN messages which were originally, say, connected to the body domain, those CAN messages are packed into the Ethernet-based network and can be then forwarded to any domain or any processing element in the car that can use that data to then create additional services and things like that. And actually, we'll have a talk tomorrow around this concept. How do we take CAN network, which is a signal-based network, and move it into, say, the next generation of software-defined and software-orientated applications and services? So how do we take those messages, move it into an Ethernet-based network, use our high-performance compute to use that from an application perspective, and then move data back from the Ethernet domain back into the CAN domain for then actuator control and things like that. So we see that feedback loop going between the CAN network, the legacy network, and the Ethernet network to compute, and then back through again.
You comment?
Yeah, I also think that even in the CAN network, the data that you're sending on the CAN network can change. I mean, the endpoints are not going to change, but the data that gets passed with a software update can change. So I think you have to look beyond an Ethernet network. You have to look at the entire network of the whole vehicle. And I think the real challenge is not knowing what that change is going to be in the future. How do you design the network or architect the network so it's resistant and still reliable, you know, with more change? Do you put more headroom in? Of course, more headroom costs more money. More bandwidth costs more money. So how much extra do you add to all your networks to look forward to say that, you know, when there's going to be a software update and you're going to need more bandwidth?
Yeah, probably so the required performance of the network is really the problem that now the conventional network depended on the domain, probably the quality and all those costs. It's a kind of balance, but if we want to reconfigure the network, then we have to make some kind of common requirement for whole network.
Well, I mean, if you add more capacity when you're making the vehicle, it's going to cost more money. Is the consumer going to want to spend more money on a network architecture that's more upgradable? I mean, That's one question. And so you have to balance the future needs with today's cost and today's marketplace. And we'll have to see. I mean, a lot of features in cars today are already designed in, and then they're just turned on. When we get to the point where we're actually making significant updates, adding whole new subsystems, that's where, it's really going to put a strain on the resources, and we're really going to have to think ahead about how much extra resources do we put in.
So maybe going to your first question on zonal versus domain. Now, it's true that you can implement software-defined vehicle with either domain or zonal architecture. It's just the question is which one will be, it will be easier, okay? And it's all about software. I think one of the advantages of zonal architecture is that it enables you to centralize what's called central computing, okay? To have, instead of one processor for each of the domain, to have one or two processors that control all the domains. And once you have these central processors, it's easier to upgrade or to update them with new firmware or new software over time when you want to upload new application, unlike when you have domain architecture, when you need to upgrade or change the software for each of the ECUs or each of the processors of those domains. Okay, so there is some advantage of moving into a zonal architecture. The other one is related to how you reshape the traffic inside the car in order to better serve new applications. Okay, and again, with zonal architecture, there is more flexibility on how you going to change the data transfer between the different processing and the ECUs unit in the car.
So you can control zone by zone, but does it mean that our requirement for the kind of processing ability will be increased, or the okay? Yes. Microphone's coming to this side.
So probably a little bit too few microphones. I think the main thing, as you see on the mobile phone, the number of sensors are not increasing as fast as the functionality increases, and it will be the same on the car. The number of sensors or input, output, actuating, whatever, will probably not increase as quick as the functionality itself increase. So the processing power, and here I don't care if it's centralized, if it's domain, if it's zonal, to get the word again. It's really, if you have the capability to process it, you can even process it in the back end by connecting via mobile. That's what really makes the difference. Having a smart functionality, having smart usage of your available data, and that's what I wanted to say in the beginning. In 10, 15 years ago, you had a linear usage of data. Now everything is using everything. And that makes the big interconnection. And that makes not really driving the bandwidth up in the first hand, but driving the processing up. And the bandwidth is coming because we want more data from the same type of sensor.
Okay.
And having it everywhere.
Maybe also a couple of cents from my side. With regards to the, let's say, efficient usage of data, there are always a very, let's say, simple solution. Put a 10 gig link and you don't care, right? But from the other side, we need to consider the costs. Because if we look at the files which are 10 gig capable, then the price is way higher. And then the question, do we really want to put such a price tag? So there are no simple solution for it. So that is why the processing of the data has to always consider the connectivity it has. So because in the end, we do not want to make it way more expensive, right? Let's say the price pressure is everywhere, and it's both on all levels, from the OEMs up to the software providers. The price tag is there, so we need to clearly think how are we going to deal with it?
Yeah, along that same train of thought, How long do we expect software-defined vehicles to be supported? What's the life of a software-defined vehicle? Is it 2 years, 3 years, 10 years? And even the communication technology for over-the-air updates is changing. You may have put a 3G radio in a vehicle and it's no longer supported. So I think you have to know upfront how long you plan to have these software updated features, and you'll have to plan for that. If we try to plan for a very long time, then it's going to really increase the cost.
Serizawa, you have comment?
So maybe back to the question, like central zone or domain free network. My idea is it's independent because the SDV vehicle is needed to updating a software, but the architecture in central zone or domain free is only for the in-vehicle network system. But the reason why we can step up to the domain free network is just very simple, like maybe the legacy ECU is hardly to give up by OEMs because it takes a long time and much cost for development of each ECU connected by a CAN or some kind of networking. That's why OEM is now thinking about to install zonal ECU and central ECU, and zonal ECU manage the legacy ECUs. In that case, it's not necessary to change the ECUs, and you can use continuously. But maybe in the next, how can I say, startup OEM, for example, maybe they don't care about the legacy ECU. In that case, they can install the all Ethernet networking and develop the ECU by Ethernet operation. In that case, the domain-free network might be appeared in the future, but SDB have to be carry out both architecture. Is my idea.
Okay. Probably it's better to pass the microphone to the Professor Ito. Time.
Thank you. So we have remained to discuss with the audience. So at this time, we want some questions from audience. If you have questions, please stand in front of the mic. Okay, thank you.
Hi, this is Karl Budweiser. I do have a question to Amir. Yeah. Amir, I would argue that you want to have as much SDN as necessary and as little SDN as possible. Therefore, you need to identify where actually flexibility and change lives. So there are components like there is software flexibility that might implement new features, right? And if I do that identification process, I end up with something like cameras. They provide a stream, and well, the resolution is fixed probably, and there is no much new features running on cameras. Therefore, I would argue that you actually want a networking technology which is customized for that use case, something like SerDes. And we had the question about what is the role of the CAN. My question is, what is the role of SerDes, and what do you think about that statement to have a customized technology which reduces the need for SDN?
Good. Okay, so someone. So anyone can answer this question?
So I'm trying to make sure I understand the question. The question is if we are using what we call software-defined network inside the car, why do we need the camera to be Ethernet based, or we can keep the camera in a SerDes point-to-point connectivity directly to the SoC as it is today, right? That's the
no, actually, to bridge them, right? Similar as the E2B, but the camera itself is not changing. Therefore, it's the technology which connects the camera does not have to provide that kind of flexibility, right? Therefore, I would rather think of naturally of actually a customized technology like ASA, yeah, and to bridge onto the Ethernet network. Something similar as we've seen from ADI with the E2B. So why not following this SerDes approach and reduce the need for SDN, thereby reducing complexity?
Okay. First of all, the assumption that if you use ASA, okay, as the PHY through the network, okay, connecting into the switches, then you are not reducing the SDN capability. You're still keeping the SDN capabilities because the cameras are not connected point-to-point anymore to the SoC. They are connected through the network, right? So you still have the capability to reshape the traffic and to send data, you know, in different direction, different resolutions, etc., right? So first of all, you know, when you compare ASA to Ethernet, then of course the question is, you know, what is the advantages and disadvantages with regard to cost, with regard to power, with regard to all the other features, the performance, okay? And, you know, we can have a discussion. As a matter of fact, we have a presentation tomorrow that is discussing it. I think the point that we make for SDN is that the camera should not be connected point-to-point to the SoC directly anymore, okay, unlike what they're doing today, but running through the network, okay? And why to do that? I guess there is many other reasons that I hear from OEM, for example, the capability to share cameras between different domains, okay? So to have, instead of having separate cameras for example, ADAS and infotainment, then you can have the same camera when it's running through the network, you know, transmitted to both the ADAS and the infotainment device. It's related to security. It's related to many features that right now, again, going back to the SDN notion of the network, make sure that the camera is not running point-to-point, it's running directly through the network, okay? Now, versus if you use ASA or something else, or as a matter of fact, you can use also GMSL through network, okay? You can take GMSL, connect to a device that converts GMSL to Ethernet, and then connect it to the Ethernet switch. You can do it with any technology, okay? APHY or any other technology, you can convert it back to Ethernet, and then from there, going through the network. The question is which one is more efficient, which technology will be more efficient in order to do that, okay? And that's a discussion that we still need to have.
Thank you.
Thank you. Any other comments or questions from audience?
Questions from floor? No? And I have one additional question is testability of the software-defined network. This morning session, somebody mentioned that too much test is not good. So if we change the configuration, then how we can test the quality of the software-defined network on this and the software-defined vehicle itself? Probably it's very difficult to make a test plan for the changing the structure or the configuration of the network. Is there any comment from somebody?
So I think we've seen a few presentations today around dynamic configuration of changing how the network operates in the car. So absolutely Ethernet can support that. I think though some of the discussions that we've had certainly are around having, say, pre-configured configurations that change based on the application or what's happening in the car. So if the car is parked, the network is configured in one mode. If the car is doing another task, then it's configured in another task, another operation. So effectively, we have a range of pre-configured configurations, which we can then test, validate, prove that they operate correctly, so that when the network is moving between those defined states, that we know that we can guarantee the operation. And that goes all the way from the configuration of the switch. How do we classify data? How do we guarantee that delivery? How do we change the priorities and everything as we move around the data? How do we change the routing of information? And as we go forward in time, we're talking about these central compute ECUs today. And let's say today we have a range of applications running on one of those ECUs. Potentially in the future, with the Ethernet-based network we have that supports forwarding the data to any compute node, we can perhaps move the applications which are running on one compute ECU to another ECU in the vehicle. You could imagine, longer-term solutions where during a fault condition, one of the ECUs is not operating correctly, and potentially we can now move services to another ECU because the network supports us routing the data to that ECU. So that again is going to add a huge amount of complexity into testing. But if we think about these kind of solutions ahead of time, that gives us a way of building test plans to then validate those solutions.
So does this mean that we need a kind of central controlling, or the how do you say, in the JASPER definition, manager or manager, MOM or something like that? A certain point of the software-defined vehicle, they have to see all the aspects of the vehicle.
I think a big aspect is we have to change our scope of testing. We don't have to finish the product and then test it, break it, fix it, and doing the cycle all over again. I think in aerodynamics, you pretty good see the shift from going to the wind tunnel to going to simulation. And the simulation beforehand, before you build something, it's growing bigger and bigger. And that's the same thing we have to do in networking. So we have to understand our network. We have to really know what it does, and then just verify that our simulation is done right. Then we can definitely handle an adaptation of the network every month or whenever we want.
Yeah, I think it's going to be difficult to foresee all the configurations that will happen, because if we truly want a software-defined vehicle that can, we don't necessarily know what's going to change 3 years down the line. So I think we really have to think about the network architecture and design it in such a way with the dynamic changes in mind. So we have to use techniques to ensure reliable and deterministic traffic where that's needed. And even if the network changes, that still occurs. And we have to make sure that the important functions of the vehicle still remain, because we certainly don't want to do a software update and be on the side of the road or cause a safety issue. So it's really important to design the deterministic and reliable functions in early, and then leave some headroom. And if those are done properly, those will continue to function as we add more best case traffic and more features in the future. And of course, all that has to be tested.
Okay, probably the comment from the floor.
Maybe the final comment with
Okay.
regards to this topic. From the software point of view, it's also very important to provide a clear separation between the applications and the networking, because then it would be easier to update the process.
Okay.
This is Fabio from Intrepid Control Systems. So from a computer science point of view, the way I see SDV is a combination of two complex problems. The first problem is a network architecture design per se, and operating system architecture design per se. Then SDV tries to merge these two naturally for obvious reasons. And we as a networking community, of course, we do have the responsibility to push requirements towards the operating system designers. But I'm asking now the entire panel, who do you expect to support us with the operating system side? So who would provide us the platform in which the networking requirements could be implemented? So yeah, elaborating a bit more and more to the technical side. So from a networking community point of view, it might be a bit far to discuss techniques on the orchestration to combine hypervisors, containers all together, which would be to the complexity of the operating system and hypervisor side. So again, summarizing, who do you think we could talk in addition to the IEEE community that could support us on that platform side to feed our networking requirements? Thank you.
Somebody on the comment on the operating system and the maintenance of the operating system and also the preparation of that.
Frankly speaking, operating system is not my main domain of expertise. However, I have, let's say, previous experience with such type of systems in my previous company. What I can say here, so first of all, to provide an efficient network is already a complex task. And if we want to include also the kind of synchronization or scheduling to the CPUs, I mean, sorry, but then it's super complex device, problem which will not be solved in the next couple of years. I'm pretty sure here. And my proposal would be to go step by step, really, because otherwise we will end up in a incredibly complex scheduling tasks here.
Yeah, but this is something that AUTOSAR would be helping us, or not at all, or this is a problem that each OEM has to take to solve by themselves, implementing their own orchestration, that then would enable SDV, then would enable us to push our Ethernet wishes.
I cannot comment here.
So to realize the software-defined vehicle, we need the performance of the network itself and also the performance of the CPU. Do you think the present performance of the CPU is enough for realizing the software-defined vehicle at present?
Well, for some tasks, for some applications, it's enough, the current performance. However, let's say the optimization in the software and also performance of the CPU cannot grow fast enough and cannot cope with the growth of the networking. And yeah, it will be mentioned in my presentation tomorrow that actually right now we need to look into, let's say, other hardware domain, in the domain of hardware accelerators. So then we can push some networking into the hardware and maybe to apply, let's say, special software to configure and to add a bit of flexibility, because then we can deal with it and leave the CPUs for applications.
Thank you. Is it almost time, or okay? Is it okay to continue the discussion?
At last 5 minutes, okay. So do you finish?
Okay.
So do you have any questions from audience? Okay. So, or any comments from panelists? Are you okay? So
the time is.
So I think the.
Yeah, we're past the. We have it. Okay, I'm sorry. We have 5 minutes. 5 more minutes.
Okay. But
I think
many people want to go.
Do you have any additional comment? Go ahead.
Oh, hi. I'm from Stellantis, Pierre Laclos, and I don't really have a question, more of a comment to add and see what you think about it. We've talked about the use of SDV for monetization, for additional features, user experience, and from where I am, mostly from what I see in France at least, there is really an exponential demand for future vehicles that are more sustainable, more lighter, more simple, and they really care about the longevity and the sustainability of the new platforms. And so the question I have is, what do you think about the mix between extremely complex features that are useful and appealing, but they require screens and displays and everything, and at the same time, there are other users which are asking for something more sustainable, simple, that lasts longer, where updates are not really needed for features, but they are needed for repairs and diagnostics and yeah, the help of lasting longer for the vehicles. So that's an open question.
So to answer this, at least in my opinion, the lifetime of current cars are increasing at the moment. So the cars are longer on the street, and that is one of the reasons we are heavily investigating in over-the-air update and in how to keep the car fresh and valid and important for the customer. One way might be just changing software. The other thing is to having standardized interfaces to change just parts of hardware. It's a little bit like Fairphone, which not really worked, but that's another topic. But you don't throw a car away every 3 years like you do on your mobile phone. It's really, you can keep it up to, let's say, 20 years, I don't know, or it can be alive up to 20 years, 25 years. So yeah, there is importance, and one of the importance is to make it still working in a changing environment. You have to find a way to keep the software up to date, and probably to change just parts of the hardware and adapt the rest of the software. On the other hand, for sure, there is a way to sustainability, and adding more and more displays is probably not the sustainable part. That's why I mentioned in the beginning, power consumption of all our communication and computing will be more relevant, and it will growing in relevance in the future. Is this the answer to your question?
Yeah, I mean, it's an open question. I'm glad we agree. We have a similar vision, but was just a way maybe to open the discussion list. But thank you. Yeah.
Okay, so in the future software-defined vehicle, we have to update the software, and also at the same time we have to update some of the hardware.
It's not a must. We can update software. We can update software in cycles, but we will grow to an end. One day in future, in the next, I don't know, 20 years, one part of the hardware will not be sufficient power-wise. And then you probably change your central CPU. I think Tesla already did something like that with its self-driving platform, make it interchangeable and having fixed interfaces. And I think this will be growing. So probably you change your display. I don't know. To add functionality and to stay relevant, you have to change both. Software you can easily change on the whole car, and you have to have the interfaces to change not the whole hardware, but just parts of it. I think Martin had a good point with the interface to the mobile world. We are now starting with 5G. Who knows if 5G is still working in 20 years? Then we'd probably have to change our antenna.
Yeah, but we can purchase mobile phones in several years probably, but we cannot purchase cars. So we have to make the lifetime to be long for this, the automotive. Okay. Any comment or question? No? Then we can close this session probably.
Okay. Okay, so it's time to close our sessions. Thank you for attendance and very interesting and great discussion. And let's go dinner.
Yeah, we can continue. We can continue the discussion during the dinner.
Please continue to discuss during your dinners. Okay. Thank you very much.
Thank you very much.